Now we'll talk about the first law of thermodynamics. Now this word right here has kind of got a lot of letters in it and it's a little hard to say sometimes, so I'm just going to refer to this as simply the first law. What is the first law of thermodynamics, or just the first law? Well, there's several ways to define this, and one way is to say that for all physical and chemical processes, the energy of the universe is conserved. So what does that mean? That means that no energy is lost or created through any physical or chemical process. So if there's a chemical reaction or there is some physical change, that's not going to change the total amount of energy in the universe. So the key words here are that energy is conserved, right? So energy is neither created nor destroyed. Now, this is simply for, or this is just for physical and chemical processes. So there are actually nuclear reactions that can change the total amount of energy, but we're not going to deal with that in this course. Another way of saying this, the same definition, is to say that for all physical and chemical processes, all energy lost by the system must be gained by the surroundings, and all energy lost by the surroundings must be gained by the system. So what does that mean? Well, if we look at our system surroundings diagram, remember that the system and the surroundings together, right? So all of this together makes up the universe. That's an arrow. Okay, so the system and the surroundings together make up the universe, and we know that the total amount of energy in the universe has to be conserved. So if any energy is lost by the system, it has to go into the surroundings. That's the only other place it can go. And if any energy is lost by the surroundings, it has to go into the system, because that's the only other part of the universe that we have. So this is simply saying that if there's energy lost by the system, it must go to the surroundings. And if there is energy lost by the surroundings, it must go to the system, which is the same thing as saying that the total energy in the universe is conserved. This definition is pretty useful to us because we're going to deal with problems pretty soon, actually, where heat is lost by one object or by a system, and you have to infer from that where that heat is going, and it's going to be going to the surroundings with respect to that system. Okay, so the last way we can define the first law of thermodynamics, which is kind of the most abstract way, is mathematically by saying the change in energy is equal to the sum of the heat and the work done by or on the system. All right, so this is a little kind of funky, I guess, to get your head around. But what this is saying is that if we simplify all ways that energy can be transferred to and from the system into two components, heat and work, then all of the energy transfers have to add up to the total change in energy of the system. And that makes sense, right? So that's simply saying that, let me see if I can draw this out. That's just saying that if there is heat lost or gained by the system, and there is work done on or by the system, then those two things together have to add up to the total amount of change in energy for the system, because we're saying that those are the only two ways that energy can change for the system. So that makes sense intuitively. It's just saying that the components for the energy change have to add up to the total energy change. But this is going to be pretty useful because we can measure this delta E, and we can measure this Q, and we can measure this W under different conditions, and we can figure out the other quantities based on the quantities we know. So if we can find two of these, we can find the third one. This is okay, so one more point. This delta E is a state function. It's a state function. So the change in energy for a system for a given process is not going to depend on how the process is carried out. Q and W, however, are path functions. So they do depend on how the process is carried out. And what this means is that if we, that's not a good color. If we are talking about the same process in the same system, and we increase the amount of heat lost or gained, that means we have to decrease the amount of work done by or on the system. So basically, to keep delta E constant for a particular process and system, we have to proportionally change the work in the heat. But delta E is a state function, and Q and W are path functions. So for example, if we have a battery, right, we have a battery that's connected to some wire, right, and we're just going to discharge this battery through the wire. So all of the energy that is stored in the battery is going to be lost to the surroundings as heat, right? In this case, Q, if the battery is our system, Q is going to be less than 0. It's going to be negative. And our total change in energy will be a loss of energy for the battery because it's losing its energy in the form of heat to the surroundings. No work is done here, so work will be 0. Work is 0 in this case because there's no change, there's no movement against a force here, so work is 0. In another scenario, we can take our same battery and we can connect it to a fan. Okay, so this is my fan. Yeah, alright, cool. That's my fan. And let's say our fan is going to move, so it can blow air and cool things off. And let's assume that there's no heat lost during this process. So it's simply powering the fan. In this case, our heat is going to be 0 because there's no heat transferred, and our work is going to be the battery is going to be doing work on the surroundings, so our work will be less than 0. Okay, so in both cases, delta E is negative. In the first case, it's dependent upon the heat. In the second case, it's dependent upon the work, and in fact, the value of delta E will be the same in both cases, but the values of Q and W are different for the different paths. So this is why delta E is a state function. It does not depend on how the process is carried out. It just depends on the system and the particular process. So in this case, the loss of energy from the battery. And Q and W are path functions because they do depend on how the system loses its energy, or if we were looking at a different process, how it gains its energy.